Hello, calculus students. This is section 6.2, the second part, looking at the trapezoidal rule. So far in this section, you've used rectangles and Riemann sums to estimate the area under a curve. We can also do this using trapezoids. So remember from geometry, the area of a trapezoid is 1/2 times the height times the sum of base 1 plus base 2. So let's look at an example that we actually did before in Riemann sums. G of x is a continuous function from 0 to 25, representing the rate Catherine travels from her home to school. G of x is in meters per minute, and x is in minutes. We're going to find the distance traveled using the trapezoidal rule. So we're actually going to have 6 different trapezoids that we'll find the area of. So my first one will run between 0 and 2. So that distance on the x is actually considered the height. So my first triangle, or my first trapezoid, will have an area of 1/2 times the height, which is 2, times the sum of the bases, 10 plus 14. Okay. Now my second trapezoid will be made up by the next two numbers. From 2 to 6 is a difference of 4. So 1/2 times 4 times 14 plus 20. Our third trapezoid goes from 6 to 8. So 1/2 times the height of 2 times 20 plus 15. Okay, our next trapezoid goes from 8 to 7. So that has 8 to 15, which is a height of 7. So 1/2 times 7 times 15 plus 30. Our next trapezoid goes from 15 to 20. It wouldn't let me move my circle, so I made that one in red. 15 to 20 is a height of 5. So 1/2 times 5 times 30 plus 20. And finally, so 1/2 times 5 times 20 plus 10. So use your calculator to add that up, and we get an approximate area of 484.5. And in units, that would be in meters, because we had meters per minute times minutes. Now, in that last example, we had trapezoids that had different heights or different widths on the x-axis. If we have all the intervals the same, we can use a formula called the trapezoidal rule. So when we find the area, we start by finding delta x. That's the width of each of our intervals. Then we're going to multiply that times the sum of all the bases. Now the bases are going to come from the f of x values. You'll notice in the formula that this first and this last value is multiplied by 1/2, because that side is only the base of one trapezoid, whereas all the other sides will be the right side of one trapezoid and then the left base of another trapezoid. Let's look at how we would do this if we think about writing it out in steps. So basically what we're going to do to use the trapezoid rule is first we're going to start by finding delta x. In order to find that, we take the interval b minus a and we divide it by n, where n is the number of equal subintervals. We're going to evaluate the function at that starting point and at each of the points as determined by our intervals. and then finally at our ending point. So the number of places we evaluate is going to depend on how many subintervals it told us we wanted. So as in the formula, we're going to add those values. And again, we're only going to take half of our first and our last value. And then we're going to multiply this by the sum of our, we're going to multiply the sum by the width delta x. Let's do one together. So we're going to use the trapezoidal rule to estimate the area using 4 intervals. If we have the function y equals negative x minus 1 squared plus 9. And we're going to look at this between the interval 0 and 4. So let's start by finding delta x. So to find delta x, I'm looking for the interval between 0 and 4. So I'm going to take 4 minus 0, and it tells me to use 4 equal intervals. So 4 minus 0 divided by 4. That gives us a nice easy one. Our intervals are going to be counting up by 1. Now we need to evaluate f of x at a variety of different points. So my interval started at 0. So that's going to be the first x value I use. Delta x was 1. So that means I'm going to count up by 1s. So 1, 2, 3, and 4. I know I'm done when I reach the top end of that interval. Now we're going to evaluate using that equation. Now to evaluate this, what we would do is we would stick each x value into our equation. So here I actually went ahead and made a table in Desmos just to show a little bit easier. So when x is 0, 0 minus 1 is negative 1, squared is 1, but we have a negative, so it'd be negative 1 plus 9 gave us 8. Okay, so then I would stick the values in for x equals 1, 2, 3, and 4. So I transferred over my values from the table. Again, we could get those f of x by just evaluating the function. Now we're ready to do our area trapezoidal rule. What we're going to do is we're going to add up those values. But remember, we only want half of the first and half of the last. So 1/2 times 8 plus 9 plus 8 plus 5 plus 1/2 times 0. Okay, that's the sum. We're going to multiply that by our delta x. In this case, our delta x was 1. And that gives us an approximate area of 26. Now remember, so far, both the Riemann sums and the trapezoidal rule are just estimating the area. So you might wonder if these over or underestimate depending upon which type of Riemann sum we do. So if we do a Riemann sum from the left hand, that means that our rectangles touch the graph at the left side of each rectangle. A right Riemann sum means our rectangles touch the function at the right-hand side. So let's look if we have an increasing function. If we have an increasing function, you can see that the left Riemann sum is going to underestimate. There's quite a bit of area that we miss because our rectangles are underneath that graph. Now, however, if we have a right Riemann sum and an increasing function, we're going to overestimate the actual area. You'll notice here that my rectangles extend above the function. As you might assume, the opposite is true if we have a decreasing function. When we have a decreasing function, our left Riemann sum this time overestimates. And for a decreasing function, our right Riemann sum underestimates. How about with the trapezoidal rule? For the trapezoidal rule, we need to look at whether the function is concave up or concave down. When the graph is concave up, our trapezoidal rule is going to overestimate. And when our graph is concave down, the trapezoidal rule is going to underestimate. This finishes your notes for 6.2. As with the last section, we're not doing my AP problems. There are some practice problems below this in your notes. Please complete those. There is a link to an answer key so you can check your work and make corrections. Reach out if you have any questions.